So one of the things we introduced last semester were waves. And so let's go back and think of what we learned then. And let's start with just the very basic idea of what is a wave. Well, a wave is a means of transferring energy from one point to another without transferring matter. So as an example of this, let's think about a wave on a string. So if you take a string, tie one end off to something, and then take the other end in your hand and just start to wiggle your hand up and down, you will transmit a wave. You'll send waves along that string. So where those waves come from is that your hand moving up and down is doing work. That work is creating energy. That energy is being transmitted along the string as the wave moves. The energy that you input into the system by wiggling your hand gets transmitted to the other end of the string as the wave moves along the string. But notice the string itself doesn't go from one end to the other. How the string is connected helps transfer that energy, but it's not like you start wiggling the string up and down and suddenly the string lurches out of your hand, jumps over towards where you've tied it off. The string stays where it is. The energy is what gets transported. So that's the idea behind saying that a wave is a means of transferring energy without transferring matter. Two basic types of waves. Mechanical waves we talked about last semester. These need a medium of particles to travel through. So water waves, sound waves, seismic waves, shock waves, waves on a string. All of these need some sort of medium. Water waves, obviously, the medium is water. Sound waves, the medium is air. Typically, though you can send sound through liquids, you can send sound through solids. And in fact, sound travels faster in solids than it does within liquids, and it travels faster in liquids than it does within air. Seismic waves obviously travel through the earth, so they're traveling through solids and possibly liquids, depending on whether or not they travel through the core. We think about shock waves typically traveling through the air. Waves on a string, again, that's the particles of the string as they're connected to each other as you wiggle your hand back and forth. So the string provides the medium for waves on a string. What we're going to introduce this semester are electromagnetic waves. And the fundamental difference is that electromagnetic waves do not need a material medium to travel through. They can travel through a medium, but they can also travel through vacuum. And so the basic question becomes, unlike mechanical waves, where it's easy to see the medium, how the particles within the medium behave relative to each other to see how that wave moves, the question becomes, if there's no medium for electromagnetic waves, then where do those waves come from? How do we create electromagnetic waves? Well, this is really building off two of the relationships that we learned about electricity and magnetism. The first is encapsulated in Faraday's law. Faraday's law tells us that a varying magnetic field is accompanied by a varying electric field. So what we said with Faraday's law was that when you change the magnetic flux through some loop, you induced an EMF. Well, that EMF came about because you now had an electric field. So in changing the magnetic field to change the flux, you created an electric field. Similarly, there's a second one of our fundamental relations in electricity and magnetism that's known as Amperes Law, which basically says the reverse, that if you vary an electric field, that's accompanied by a varying magnetic field. If you change an electric field, you're going to induce a change within a magnetic field. So putting these two things together, we get electromagnetic waves because they're formed when you have a varying electric field that couples with a varying magnetic field. So if you think about this picture, what this is showing is we have an electric field that's varying along the x-axis. So that's the blue one, and you can see how it's 0 here, it gets stronger up to some maximum value, comes back down to 0, gets stronger pointing in the other direction, comes back to 0. So we have an oscillating electric field that's bouncing back and forth in the x direction. That's been coupled with an oscillating magnetic field that's bouncing back and forth in y. So initially it's 0, but that magnetic field comes out towards us in the y direction in this particular choice of coordinate system. It gets stronger, it then goes back to 0, it then starts going away from us, again reaches its maximum value, comes back, reaches 0. So what I have is I have an oscillating electric field that's paired with an oscillating magnetic field. And when I have that, I end up creating an electromagnetic wave that travels in the z direction. So what we're going to tend to do is talk about the oscillations in the electric and magnetic field are going to happen in the xy plane, and then our wave is going to travel in z. And so a couple important points to recognize from this figure. The first is that the electric and magnetic fields are perpendicular to each other. The second is that the wave travels in a direction that's perpendicular to both the electric and the magnetic field. In this case, we've got the electric field oscillating in the x direction, the magnetic field oscillating in the y direction, and the electromagnetic wave is traveling in the z direction. The next important point about electromagnetic waves, they travel at constant speed. And you know what that speed is. It's called the speed of light. So as we'll talk about in the next section, light is one particular sliver from the electromagnetic spectrum. So light is a type of electromagnetic wave. So the speed of light, the speed at which light travels, it ends up being the same speed that all electromagnetic waves travel at. We typically use c, as in E equals mc squared. The c in that equation is the speed of light. It's calculated, oddly enough, by 1 over the square root of, this is epsilon naught and mu naught. So this is one of the constants that we were dealing with thinking about electric problems. This is the constant we were dealing with thinking about magnetic problems. So one of the things that's interesting about the speed of light is that it shows us this partnership between electric and magnetic fields that's creating your electromagnetic wave. When you plug all this into a calculator, plug in your values for epsilon naught and mu naught, take the square root, take 1 over that value, you end up with something that ends up being just slightly less than 3 times 10 to the 8th meters per second. So the three significant figures, it's 3 times 10 to the 8th meters per second. You'd have to go all the way out to 4 significant figures to see that it's just under that value. It's 2.998 times 10 to the 8th meters per second. Of course, since this is a constant value, that means if you want to figure out the distance traveled by an electromagnetic wave, we can use our constant velocity expression. So the distance a wave travels is going to be equal to the speed of the wave times the time you let it travel. And so the speed of light in meters per second, that's c in this 3 times 10 to the 8th meters per second, will let you calculate out how far your wave travels in meters if you know how long it traveled in seconds. The last thing we want to show is that there are two ways that we can kind of plot out what's going on with an electromagnetic wave, and this isn't any different from what we plotted last semester in talking about mechanical waves. We can plot the wave disturbance as either a function of time or a function of space. And so this top one is showing us how if you looked at some particular point in space as the wave moved through, you would watch that point in space oscillate up and down in either what you called the x or y direction. It's going to oscillate within the xy plane as a function of time. And so if you have a plot of your electromagnetic wave as a function of time, you can read off two important values. The first one is the amplitude, right? What's the peak of the wave in terms of its electric field or magnetic field, depending on which field is shown oscillating within the plot that you're given. You can also see the period. So again, the period is what chunk of time does it take to go from peak to peak within your wave, or trough to trough within your wave, or from some midpoint through the midpoint again and back to the midpoint a second time. So at the 0 point, but on the same part of your wave. So if you start on the wave angling up, you got to get back to the point where the wave is angling up. That gives you the period. On the other hand, if what you have is, again, your disturbance somewhere in the xy plane, but now plotted as a function of position. So this says take a snapshot. So some instant in time, take a picture. Here's what either the electric or magnetic field of your wave is going to look like as your wave is moving in the z direction. And so, of course, in this case, you can still get the amplitude, but now because you're reading off not something in time, you're reading off something in position, this tells you the wavelength of the wave. And of course, the period and the wavelength of the wave we can use to find a different way to calculate out what the speed of light is. So the speed of light, which is fixed, is equal to the frequency of the wave, which is 1 over the period. So that's why knowing the period is important, because its frequency is 1 over the period, times the wavelength. So here lambda is the wavelength, f is the frequency, and frequency times wavelength tends to be the most useful way for us to calculate out what the speed of your wave is. And of course we know for electromagnetic waves that that's going to be equal to c.